maple. Um, Okay, I think we're ready to begin with day 12 today. Just for those of you that are physically here in class today, Maple does meet tomorrow. Our first Maple lesson. It's my understanding I need to change the deadline on what's out there, but don't worry about a deadline yet. Once I get things changed, I'll inform you of the deadline. But we will talk about some basic Maple commands. What I do urge you to do is to go to the math department homepage sometime between now and tomorrow. And if you go to the math department homepage, www.math.ncsu.edu, so that's the math department homepage. And right down here, you'll see a link to Calculus with Maple. And click on that if you haven't done that already. And I think it would help you to kind of browse through some of the commands that we're going to take a look at on this first day. These commands in this Maple lesson can be done at any time. It's not specifically targeted to go in, chapter 2, section 1. So we could do this basically at any point in time. And it may not match up exactly with what we're doing, but the Maple that we do for 141 is to kind of get you used to the syntax and the commands. And then when you get to 241, when you can use it with Maclaurin series and power series, and it really becomes helpful, you'll know some of the basics. And then most importantly, when you get to Calc 3, which I think probably most of you, if not all of you in this class, are headed that direction, then things that are multivariate, that are three-dimensional in nature, I think you're going to really rely on Maple quite a bit. Because it's hard to visualize these three-dimensional surfaces. Maple can be very helpful in that. But take a look at that before tomorrow. We are going to begin chapter 2 today. I guess this is technically the beginning of calculus in here, although we're kind of still flirting with some pre-calculus ideas, but it's right on the verge of calculus. When you start looking at limits and start talking about average rates of change and instantaneous rates of change, then we're kind of moving into calculus at that point. So let's take a look at chapter 2, section 1. I don't always say this, and I probably should say it every class. I think it's important for you to read this material that's in the book. I read it when I prepare the first time, and I usually, when I'm eating lunch, ready to come over here to actually teach class, I usually scan it or read it again. It's not a difficult text to read. I've participated with a lot worse texts as far as how they read. This is pretty well written. So read the material. I'll try to summarize today some things that are in that material, but I can't do it justice in all cases. So make sure you read the material. As we start talking about calculus, we start talking about a tangent line. And as we embark into calculus and we start talking about a tangent line, more specifically the slope of that tangent line, it might be a surprise to you that have never had calculus before that curves have slope. We all know that lines have slope, but curves have slope as well. The only thing that we need to be prepared for with regard to the slope of a curve is that the slope of a curve changes depending on where you are located on that curve. So we could have a curve that looks like this in the plane. That would be a typical cubic polynomial. So when we talk about the slope of a curve, we're really talking about the slope of a line that's tangent to the curve. So if we want to talk about what the slope of the curve is at this point, What we really want to do is construct a tangent to the curve and then evaluate the slope of that line, that tangent line. So the idea of tangency, you probably first encountered that in a high school geometry course when you talked about a line being tangent to a circle, which was just resting up against the circle. It's the same concept. You do have to pay attention to it here because a tangent line, although it's tangent in one area, if you extend it to another area of the curve, it might actually meet the curve again. So the idea of tangency means in that general vicinity. For example, if I want the slope of this tangent line, I want to come up with a line that's tangent to the curve, just like I did before. Now, if I would extend that, that would meet the curve in another point. That's legal. That's fine. We're still going to call that a tangent line, even though it does physically meet the curve at a later point, because we're only concerned about that tangent line in this general vicinity. A little bit to the left of there and a little bit to the right of there. Would it just rest up against the curve in that small locality? You can probably guess where some of the more important tangent lines would be located, and those would be where a curve changes direction. So if you can find those points, you know quite a bit about a curve, because the curve, what does it do? It's decreasing. Its rate of decrease slows down to where it's not decreasing at all at this point. And in fact, as it leaves, it increases very slowly and then picks up the pace. So you can see the curve begins to become flat, and then in fact is flat for just an instant, and then kind of eases out of there very nearly flat as well. So if you can have a graph and you know nothing else about that graph except where the tangent lines are horizontal, let's say, for example, the tangent line is horizontal there and there. Well, there are some things. There's one thing that you know this curve has to do. First of all, if it's continuous, it has to connect that dot to that dot. And it leaves here fairly flat, and it has to decrease and enter here fairly flat. So that much of that curve is absolutely determined, just based on where the tangent lines are horizontal. Now, what could it do leaving here? It might leave here fairly flat and increase. It might leave here fairly flat and decrease, right? We don't know where it's headed necessarily. We don't have a dot to go toward. It could increase into here, flatten out, or it could decrease into here and flatten out. Again, because we don't have that extra point over there, we're not quite sure which it does. Does it decrease into there, or does it increase into there? But this portion of the curve, from this point to this point, is clearly determined based on the slope of the tangent line. There's no way it can connect this dot to this dot, be instantaneously flat here and flat here without looking just like that. So there's quite a bit you can determine about the curve based on what's happening on the tangent to the curve. So we are initially going to study slopes of tangent lines to curves. Unfortunately, you know this definition of slope just like I do, and at a point is not going to work, because don't we need 2 points to find slope? Isn't it the difference of the two y's over the difference of the two x's, right? So it doesn't seem to make sense that we could have a slope at a point. So we have to approach that kind of problem in this fashion. So what we really want is to know what's going on at that point, at that single point. What we have to do is, and this will be over-exaggerated here, we'll find the slope of the secant line. Does that word ring a bell? The secant? Secant meaning 2 points, right? Again, back to high school geometry is probably the first time you had that. You had a circle and you sliced through that circle in 2 points of intersection. That was called a secant line. So if we start with 2 points, we have the slope of the secant. And just like slope has always been the difference of the y's over difference of the x's, we have 2 points, we have 2 x's, we have 2 y's, we can actually plug them in. And And you might think, well, that doesn't do us any good. We want the slope of the tangent. Well, what we have to do is take this second point and gradually bring that second point closer and closer and closer to the first point. And then there's practically no difference at all between the first point and the second point. They're basically side by side. And our secant technically still is a secant, but it's practically a tangent. So we start with the slope of the secant. We let our 2 points get closer and closer together till they are, for all practical purposes, 1 point. And then we no longer have the slope of a secant. We have the slope of a tangent. So let's do that. And I don't usually like to use the examples that are in the book, but sometimes I do because they're just so good and so basic and so classic that I feel like that's just a great problem to start with. So they use y equals x squared, and that's such a familiar graph that I think I would like for us to start with y equals x squared. Now I graphed this using Maple, so this is one of the things that we can use Maple for, is to plot points, not that we need it on something like y equals x squared. But I want to start with that example. Let's say that the goal is to find the slope of the tangent line at the point 1, 1. Slope of the tangent line at the point 1, 1. So using slope, as we know slope at this point in time, one of the ways we could get an approximation for the slope of the tangent, why don't we take two secant lines? Why don't we take the slope of the secant and use 1, 1, and let's go a little bit to the right of 1, 1, or at least a little bit to the right of the x value 1. And let's say, let's just go a quarter of a unit over to the right. So I know what my final destination is, to know what's going on at x equals 1, but I need another location, so let's go over to where x is 5/4. What's the corresponding y value? When x is 5/4, what's the corresponding y value? What is every y value in terms of x? It's the square of the x, right? That's why I wanted to start with this example, because it's so nice just to, whatever the x is, square it and you get the y. So what, 25/16? And then that tells us what's going on from 1, 1 to a little bit to the right of 1, 1. Now let's see what's going on from 1, 1 to a little bit to the left of 1, 1. So I want to back up a quarter of a unit. So let's say x is 3/4. What's the corresponding y value? 9/16. So do you think if we found these two slopes and averaged them, that might be a pretty good guess as to what's going on at 1, 1? Because we go a little bit right of the x value 1, a little bit left of the x value 1. Maybe if we found them and averaged them, it would give us an idea what's going on at that value x equals 1. Well, let's do that. Let's find the slope of the line that contains these 2 points. 25/16 minus 1 and 5/4 minus 1. I'm going to need some calculator help here. What do we get? Maybe not. We'll just see what happens. 25/16 minus 16/16 is what? 9/16? Mm-hmm. And 5/4 minus 4/4 is 1/4. So what do we get out of that?
9/4.
9/4? Does that look right? So using those two, the slope is 9/4, which is what, 2.25? That's probably a little too steep because we went to the right. And what happens to this curve as you move out to the right? Doesn't it get steeper and steeper? So that's probably a little too large for the slope. Let's see what we get down here. 9/16 minus 1 and 3/4 minus 1. What do we get? Negative 7/16 and negative 1/4. 7/4. We still on the screen there? Now, would you say that's probably not quite enough? We're off to the left of the 0.11 where the curve is less steep. So 7/4 is probably not enough. 9/4 is probably too much. Well, let's take the two and average them. Which the average of 7/4 and 9/4 is 8/4, right? Is that right? Mm-hmm. 2? Now, it just so happens that this curve is so simplistic that, in fact, that is exactly what's going on at the 0.11. Now, you're not going to get an exact answer all the time, but it ought to be fairly close to the slope of the tangent at the specific point. And the point that we're talking about is the point that I used in both of them. 1,1 is the point in question, so to speak. We went a little right and a little left of there, and then we'll take those two results and find the average. That's one way of approximating what's going on at a certain point. So could that be the slope of the tangent? Well, in this case it's exact, but in most cases it should be a pretty good approximation for the slope of the tangent line at the 0.11. Do you see the difficulty with putting in the 0.11? And then let's choose the other point to be the point, how about 1,1? What's the difference of the y's? 0. And what's the difference of the x's? 0. So we end up with 0 over 0, which is one of those bad values, one of those indeterminate forms. So we can't just choose a point. We've got to choose another point. We want to make sure it's fairly close to the first one. So what we hope we find is the slope of the line that's tangent to the curve at the point. And let me just put the slope is approximately 2, and we'll see in a little bit that in fact the slope is 2, exactly. Okay, let's continue with another approach. Really, I guess probably 3 approaches today to finding the slope of the tangent. Same function, and I still want to kind of focus in on that same point. Let's try this approach where we take the point 1,1, so it's the same curve. Let's take the point 1,1, and let's take kind of any other point. And I'm going to pick the point x. So I want to leave it open. I want the second x value to just be kind of wide open. X, comma, well, you tell me what the y value is. What do you do with any x value to get its corresponding y value? Square it. So if the x value is x, the y value is the square of x. And here's the point 1, comma 1. Let's take the slope of this secant line and then try a little algebraic manipulation and see what we can find. So there's our 2 points. So what is the slope of the secant? Well, let's take the difference of the y's over the difference of the x's. So x squared minus 1 and x minus 1. You can see a little algebra developing here, which is going to be kind of handy. Now, we're not going to get a formal definition of limits today, but I think you've encountered some limits prior to this course. Let's see what happens to this result, this slope of the secant. What do I want to happen? Well, what I really want is I want x to be real close to 1, don't I? As long as x is real close to 1, then we're talking about what I really want is the slope of the tangent. So let's take a limit. Let's see what happens to this quotient, x squared minus 1 over x minus 1, as x gets closer and closer and closer to 1. Now this is technically a two-sided limit. X can get close to 1 from numbers a little larger than 1. So it could be 1.1 and then 1.01. So I'm getting close to 1, but the numbers are a little larger than 1. Or you could be less than 1, and the numbers could also be getting closer to 1. So we need to be able to approach 1 from both sides. So probably you were itching to do this from the time I wrote this down. What do you want to do, and what do I want to do algebraically to this result? Factor and cancel, okay, or factor and reduce. So the numerator is the difference of two squares. Factors as the sum and difference of the square roots. Now, before we kind of do the thing we want to do here, and that's cancel or reduce, can I always, or can you always reduce x minus 1 over x minus 1? Is that always 1?
Is that what you're talking about?
No, just what is x minus 1 over itself, is that always 1? So can I kind of slash the numerator?
No.
When would x minus 1 over x minus 1 not be 1?
When it's 1.
When x is 1, right? See that? Because we get 0 over 0, and we know that to be a problem. You can 0 over 0 is anything you want it to be. So that's clearly a problem. Now, if x is approaching 1, and again, we'll hit on this quite a bit harder later in Chapter 2, but if x is approaching 1, does that mean x is not 1? Yes, it does. X is approaching 1, but x is not 1. So as long as x is not 1, then I can say this is some number, non-zero number, over itself. Any non-zero number over itself reduces to 1. So what are we left with?
Plus,
We're left with, after we reduce x minus 1 over itself, realizing that x can't be exactly 1, we're left with x plus 1. Now if x is very, very, very close to 1, what's the result? Doesn't it get very, very, very close to 2, right? Now do we get 2? Not technically, I guess. But as x approaches 1, it's okay to say that the limit is 2. That's permissible. The limit is 2. Now 2 happened to be the number that we actually got by averaging the 2 before. We got lucky because it's a simple problem, but there's some algebra that you could evaluate the limits with. This time it worked out really nicely where the numerator factored and we can reduce like factors. Any question about this? Can you see on the picture what happens as x approaches 1? Doesn't that mean the second point is getting closer and closer to the first point?
Mm-hmm.
Is that okay? If x is getting closer and closer and closer to 1, then it's coming in here. And that's what we want to happen, because we're looking for the slope of the tangent. Okay? And let me put this back in here because we did switch horses here, right? We started with the slope of the secant, but as soon as we let x get closer and closer to 1, we're not talking about the secant anymore. We're talking about the tangent. Tiffany?
Which method is best to use then?
You're probably not going to like this answer, but neither of these.
Okay.
Okay? We'll actually eventually we'll get a better method than all of these. They're just trying to get you thinking in the idea of starting with a secant, letting the 2 points get closer and closer, and then we'll eventually get with the tangent. This one is not a bad method because it does involve some algebra and we can get there fairly quickly. We don't have to plug and chug so many numbers. But we'll actually get a method that's better than either of these, and in fact, the next one we're going to do. If we want to know what's going on at 1, then one thing we can do is see what's going on very, very, very close to 1. So here's another option, and you can do this from either direction. So what we really want is the slope of the tangent at the point 1, 1. Same thing we've done on the first 2 examples. The first time we found 2 on either side and averaged. The second one we did a little algebraic manipulation. And this is a process that I think gets at kind of the heart of what we're trying to do. We're going to start with the slope of the secant. And then what we want to happen is for the 2 points to get closer together. And then we'll be talking about the slope of the tangent. What's happening at a certain point? Now let me provide you a couple of words that are provided in the text that as you read them you'll familiarize yourself with the words. But the slope of the secant your authors will refer to, and I'll refer to, as an average rate of change. Now, doesn't that make sense that we have 2 points in time and we want to analyze on the average what's happening between those 2 points? Now, does the curve really follow the straight line between those 2 points? No, it doesn't. But on the average, that's what's happening as you go from point 1 to point 2. And when you get out here, they'll refer to this as an instantaneous rate of change. Now, doesn't that sound like we want to know what's going on at a certain point, right? At that instant? See that word in there? At some instant that we're trying to kind of freeze that instant in time. What's going on there? Not what's going on average from point 1 to point 2. What's going on at that point? So if they refer to an average rate of change, then we just want to put in 2 points on the curve and calculate the slope. But if they want an instantaneous rate of change, then we have to go through this limiting process. So here's another way of going through that limiting process. You'll probably be sick and tired of this curve when we're done, but it's simple enough where we don't have to battle a whole lot. So let me go back here to what we want. We want the slope of the tangent at the point 1, 1. So let's start with, let's let our second x value get closer and closer and closer to 1. So let's take 1, 1, and let's say 1.5, 1. Excuse me, 1.5, the square of 1.5. Then let's get a little closer. So instead of 1.5, let's say 1.25. And let's get a little closer even still with the next point. So 5/4, what do I want here to get 1/8 of a unit away? 9/8. what would that be? 81/64. But it needs, clearly needs some calculator help here. Let's just get decimal approximations as we go. Let's do one more. What would that be? With sixteenths, what would that be?
17 sixteenths.
17 sixteenths. 17 squared is what? 289 over 256. So, am I letting the second point get closer and closer and closer to the first point? I'm trying to with these. So what is the slope? Here it is 9/4 minus 1, 3/2 minus 1. Here it's 25/16 minus 1, 5/4 minus 1. 81/64 minus 1, 9/8 minus 1, 289 over 256 minus 1. Now we know what we're supposed to get. The first time we took them and averaged them and got 2. That's reasonably close. In this example, it's exact. The second one, we took an algebraic approach and got 2. The slope of the tangent at 1, 1 was 2. What do we get here? Five-fourths over 1/2. What's that? Somebody's got a calculator handy. Let's just get some decimals here.
2.5.
What is it?
2.5.
2.5?
Yeah.
Okay, and that's probably exact, but I'll just keep my approximation symbols there. How about the next one? 2.25. Next one? 81 over 64 minus 1. Divide that by 1/8. Now, are we getting results that we should be getting? Right? Aren't we supposed to be getting closer and closer and closer to the slope of the tangent, which we already know is 2? And what about this last one?
Is that 17 or
17 over 16. So 2.0625. So what should be happening is that we're getting closer and closer and closer to the actual value, which is 2. So you can come in from the right, which we just did, or you can come in from the left, and I'll spare you the arithmetic there. The same thing works. Now, can you tell me what would happen from the left? What would the slopes be?
Decrease. They're starting.
They'd be increasing, right? And wouldn't they be less than 2 and getting closer and closer to 2 from the other side? So we're larger than 2, and as we go, we're getting closer to 2 from the positive side. If we did this, the other piece of this, we'd be less than 2, and they'd be getting larger and larger and getting closer to 2. So that's really kind of 3 different ways to evaluate the slope of the tangent. The last piece of Chapter 2, Section 1 talks about the relationship between distance and velocity. Let's say that, let me just make up a problem. Let's say that an object is projected from the ground. It's projected up into the air with an initial velocity of 64 feet per second. And then after it's projected up from the ground at this velocity, the only thing that acts on this object is gravity. And acceleration due to gravity is negative 32 feet per second per second. Is that a term that you're familiar with? It doesn't matter. We'll get more familiar as time goes in this class. But the height of that object, so typically an s of t will be a distance or a height or a position type function. So t is time. Let's say for this problem with what I just described, let's say that the height of this object at any time t is described by this equation. So t is in seconds. S of t will be in feet. T will be in seconds. So it's projected off the ground. How do you know it's on the ground? Somebody want to take that equation and how do you determine that, in fact, what I said is actually true?
If you take time seconds before it's let go 0, the whole equation equals 0.
Okay? At time 0, right, is where the clock starts to tick on this problem. At time 0, the s of 0, that ought to be its height or distance above the ground or position at time 0. Which in fact is 0. So it's at time 0, its height is position 0 on the ground. And we could plug in some different values. The s of 1 ought to tell us where this object is 1 second after it was projected upward. So where is it? What is its location or position or distance or height? It's all of those at time 1.
48.
48 feet? This is feet also, right? And we could continue to plug in different times, and it would give us the location of the object at that particular point in time. Now let's suppose that we wanted to know the average rate of change, and let's just use the 2 points that we have here. Let's not. Let's do this. Let's get one other one. So at time 1, this object is 48 feet off the ground. Where is it at time 2? $64 feet off the ground. Everybody all right with those computations? So that's just a position. We have a position function. We plug in the time, and it tells us the position. Now let's take these two, and let's just take them as points on this function. By the way, you know what that looks like, don't you? If you were to graph that function, what would that look like? Parabola. Tell me something else about it. Opens down, right? Isn't that kind of what happens if you let the clock run here? It starts out at point 0, it's projected upward. Its initial velocity kind of loses all of its power because of what? Gravity. And then it falls back down, so we've got this nice little parabolic path. So you should recognize that as a parabola. Gosh, maybe that's why we study parabolas. So that when we see stuff like this, we recognize what it is. So let's take the s of 1, which is 48 feet, and the s of 2, which is 64 feet. Now, so this is really a point. When we plug 1 into the function, it kicks out 48. And when we plug 2 into this function, it kicks out 64. You know, that's probably not descriptive enough. Let me do a little bit more with that. When we plug in 1 second, it kicks out 48 feet. And when we plug in 2 seconds, it kicks out 64 feet. Now you may think I'm stupid, which you're not so wrong with that. But I do want to talk about units here. What if we took the slope here? We got 2 points, right? Slope of a secant that connects these two. 64 feet minus 48 feet. Back here to 2 seconds minus 1 second. What do we get? Okay, you're a couple steps ahead of me. He said a velocity. Isn't that correct? We started with a distance function. We kind of put in some values and found points on the distance curve. But in evaluating the slope on the distance curve, we end up with something, and that's why I wanted to include the units, because it's hard to disguise this when you look at the units. 64 feet minus 48 feet is what? 16? What? Feet?
Feet per second.
And 2 seconds minus 1 second is what? 1 second. So it looks to me like we have 16 feet per second, and that is a velocity, right? So is that an average rate of change in this regard? That's an average. So on average, going from our first point, 1, 48, to our next point, 2, 64, we've got an average rate of change, or an average velocity. Does that make sense? An average velocity of 16 feet per second. So during that 1 second interval, we gained 16 feet of height. Is that okay? So it is fairly descriptive in that regard. Now suppose we wanted to find out what's going on at 1, 48. We want to know this time that's a different question, isn't it? A little bit different. Now, could we use our data somehow to generate what's going on at 1, 48? Well, we just had a couple of methods, right, that we could do. We could find some values close to 1 and then get closer and closer and closer to 1, right? That would work. So we could, in fact, find out how fast that object is going at that very instant in time by several different ways. Now, I want to propose another one here that we haven't seen yet that will kind of lead us to our so-called definition of instantaneous rate of change. This, by the way, would be instantaneous velocity, right? The velocity at that instant. Yes, sir?
Can we use derivatives for that?
Yeah, eventually that's where we're headed. In fact, a derivative, what Umair just said, a derivative is the slope of the tangent. And that's where we're headed. And that's when you get to a derivative, then you're actually technically doing calculus. Let's try this. This is our last approach today. We have this function, this distance, height, or position function. This would be a free-falling object, and nothing is in this equation for air resistance. So we're neglecting air resistance here. So that was the function we had, right? And we've decided if we plotted points on this thing, 0, 0, 1, 48, 2, 64, is that right? That we could get this thing to be a parabola. We would expect it to be a parabola that opens down. Let's just take a point here. And let's say that, probably jumping a little bit too far here, but I don't want to belabor all the numerical calculations because that gets old very quickly. Let's say that I'm going to pick an initial time, and just to keep it simple, I'm going to call it t. What's the corresponding y value, or s of t value, when t takes on the value t? Okay? Is that okay? Now, on this same curve, I don't want to get too far away from t, so I'm going to slide over h units. I'm just picking a letter that's consistent with what's in your book. So I want to start at t and just slide over a little bit, h units, some increment of t in this case. Now I'm at the t value t plus h. What is its corresponding s of t value?
Oh, there's a t, but t plus h.
Okay. Wherever there's a t, plug in a t plus h. So it ought to be what? Negative 16
T plus
t plus h squared plus 64
Times 2.
t plus h. Okay, and let me write these points down here. There's our first point. Second point is first element t plus h, second element, same function, replace t plus h for t. Everybody okay with that? A little more complicated than numbers, but it's the same concept. Now, what do I want to do? I want my second point to get closer and closer to my first point. How would that happen with what I have set up here? What would have to happen to h? Let me rephrase that question.
had to approach 0.
Yes. Is that okay? If h got smaller, wouldn't my 2 points get closer and closer together?
Mm-hmm.
So let's take, if what we really want is the slope of the tangent, let's take a limit. Difference of the y's, or in this case, the difference of the s of t's, over the difference of the t's. So it's a slope, and if you remember nothing else today except that anytime you start with 2 points, you can always take the difference of the second elements, divide it by the difference of the first elements, and you always get a slope, whether it's a slope between 2 points or the slope at a certain point. And what we want then to happen, for this to become the slope of the tangent, we want h to get smaller and smaller and smaller. That way the 2 points get closer and closer and closer together. So technically right now we have a secant, but as h gets in here closer, we, for all practical purposes, will have a tangent. We want the 2 points to be basically side by side. Now, does that look like a horrendous algebra problem? It might look, I mean, its bark is a whole lot worse than its bite. It might look bad, but hopefully all of you feel reasonably competent in algebra. That's an algebra problem, isn't it? Until the very end. I mean, I know that all of you have this capability. I'm confident that you could square t plus h, and we're not going to do it all, but there's a t squared plus 2th plus h squared. We've got 64t plus 64h plus 16t squared minus 64t. Well, the denominator is really easy. What do you get in the denominator? What's the difference between t plus h and t? Gosh, I can even do that. That's just h, isn't it? Isn't that what we set up by design, was the difference from our initial t value to our next one? That's by design. So that's just h all the time. Now we're still going to get something that has what in the numerator? Feet. And has what in the denominator? Seconds. So it's still feet per second. It's still a velocity, but this time it's an instantaneous velocity, an instantaneous rate of change of distance with respect to time. Does that sound like a velocity to you? Instantaneous rate of change of distance with respect to time. Distance divided by time ought to be a velocity or a rate. So you'll see a lot of algebra, a lot of simplification that can be done, but this is the direction we're headed. And Umair said that we might as well call it what it's going to be called. It's going to be called a derivative, and it's nothing more than the slope of a tangent line to a curve. I'm sorry about belaboring the x squared example. They actually switched to a second example in the book, but I thought we could probably use that simple one and just carry it right on through. Problems that I picked out, I didn't pick out a lot of them. I'm sure you'll be disappointed with that. These begin on page 99, and I think it's 2, 3, 5, and 8. 2, 3, 5, and 8. And that concludes lesson 12, and we will be in here tomorrow for Maple.